Okay, here we've got a question where we've got a distribution of pebbles, or we've got a mean, so we've got a mu. We've got a standard deviation, so we've got a sigma. Okay, but almost to start with the end of this question first, what we're not told is that the weights of these pebbles are normally distributed. Okay, so I am going to be working with a normal distribution, but I need to justify it. Okay, now if the original population is normal, then you just go ahead and work with normal distributions and there's no problem. But if that's not normal, then we do need this gizmo, the central limit theorem, and that only applies if n is reasonably large. So that's why the fact that sample sizes of 50 pebbles is going to be important. So I'm going to want to set up a central limit theorem, but I can't say that the weight of a pebble has a normal distribution. All I can do is say that mu equals 48 and sigma equals 8.5, but because n is large, okay, then I can set up a normal distribution for means of samples. And if I look at this, I'm not finding out probabilities about individual pebbles weights. I can't because I don't know the distribution, but I can find out probabilities connected with the mean weight of a sample of 50 pebbles. So I can set up a distribution for x bar, which is the mean weight of a sample of 50. So that is going to be a normal distribution. Now the central limit theorem tells me that the mean of this distribution is the same as the original mean, but the standard deviation, or sorry, the variance is sigma over n, but the standard deviation, which we call the standard error, is sigma over root n. Okay, so the mean I'm working with is mu, which I'm told is 48.6, okay, and my standard error, sigma over root n, equals 8.5 divided by the square root of 50. And I might as well get that as a decimal, so trusty calculator will tell me that 8.5 over the square root of 50 equals 1.202. Let's go with 4 significant figures for now. Okay, so 1.202. So now this is going to be the distribution I'm working with. So I want a value of 49.0. I need to draw a sketch showing that value and where it is in relation to the mean. So the mean in the middle is a value of 48.6 for a z value of 0, and I want to work with 49.0, that's going to be above the mean, 49.0, and I want to work out what the probability is of being less than that, so here's the area that I want to work with. But in order to look up this probability, I need to find the z value for this. So I'm going to use my formula for z. Z equals the value minus the mean over the standard deviation as usual, but this is now the distribution of means, so it's actually an x bar value minus the mean over a standard error value, where the standard error is this sigma over root n. So for part A, that's what I'm doing here, I'm going to be doing the value of the mean, the given value of the mean, the cutoff value is 49, minus the mu value, which is 48.6, over the standard error, which is 1.202. That's where my z value is going to come from, so let's work that out. So I've got to do 49 minus, I could do this in my head, 48.6 is going to be 0.4, isn't it, over 1.202 equals this number here. This is a z value of 0.33. I'll go 333, but z values is often we round them to 2 decimal places. Okay, and that makes sense on my diagram that this is 0.33. Because it's a positive z value. Good. So I now need to look up the probability to the left of that. Well, normal tables like telling me the probability, my calculator likes telling me the probability of any range I tell it, but I'm going to have to put in a large negative value for the left-hand limit. So let's do that. So I'm going to go into distribution mode. I now want normal CD for 2. My lower limit then, so I want to start from something like minus 500, and my upper limit I'm going to have as this 0.33. And I should get a probability of more than a half. Let's see if I do. Equals 0.6293. So P equals 0.6293, which does seem reasonable for this probability of more than a half. So that was part A, and part B is going to be a similar kind of exercise. So B, okay, now I want the probability that the mean weight will be 47.0 or less. Now, throughout the normal distribution, this was less than, this was a weight or less. It doesn't matter whether it includes the 47.0 because the probability of any individual outcome is 0 anyway. So the nice thing about normal distribution questions is I don't have to get too hung up about whether the 47 is included or not. So once again, I've got 48.6 in the middle for a z value of 0, but this time my 47.0 is going to be this side of centre, so that's 47.0, and I want the probability of it being that value or less. So I'm going to do the same as I did before. I'm going to get my z-score, which is the x-bar value minus the mu value over the standard error. This is an x-bar value, a mean weight for the sample of 47.0. Take away the mean of the population, 48.6. That's my mu. Divide by my standard error, which was sigma over root n, which I've already got is 1.202. And I'm going to get a z value of, calculator says, minus 1.33. Does that make sense on my diagram? Minus 1.33. Yes, it does, because here's 0. I want a negative z value, minus 1.33. So my limits are, again, I want a very large negative value, somewhere below minus 1.33. So I need to do normal CD, and my lower limit is going to be minus 500 or 5,000 or whatever I want, huge negative value, and my upper value is now going to be this minus 1.33, and we get a 0.09175, so I'm going to get P equals 0.09176 I'll settle for. And does that make sense? Yes. This looks like a probability of much less than 1, so I believe that value. So I've done A, I've done B. I haven't written down my answer to part C, but it says, explain if I needed to use the central limit theorem. And the answer is, I did not know that the original distribution of pebbles was normal. So the only thing that allowed me to use this normal distribution here, okay, is the fact that I had a sufficiently large sample. So yes, the central limit theorem was used because the parent population was not known to be normal. Okay, and luckily I could use the central limit theorem because n as 50 was fairly large.